Welcome to this development tutorial on the Binance Smart Chain using Hardhat. Today we will be creating a smart contract to freeze a token within the Binance Smart Chain for a determined time, after which the wallet owner of the funds will be able to withdraw with an added percentage of interest for the time funds were locked, like a small D5. This tutorial is a continuation of our previous video, creating your token on the Binance Smart Chain. Complete guide with Hardhat Quicknode, where we learn how to create an ERC20 token using Hardhat and a Quicknode RPC for the Binance Smart Chain. Quicknode offers secure, fast and reliable nodes for Web3 development, as well as other specialized services such as token and NFT APIs across multiple blockchains, a blockchain alert service called Quick Alerts, and IPF storage services for your projects. Go to quicknode.com to learn more and start enjoying their services. Let's open our repository where we have created the ERC20 token using Hardhat and review our Hardhat config file again. Remember that we are provisionally working on the Binance testnet as the default network. And in the networks parameter, we have this network configured with our Quicknode RPC and our secret phrase, both taken from the environment variables in our .env file. We also have the address of the ERC20 token that we have created and that we will be using for our small finance system to date. So let's create a new file called tokenlock.sol. In the contracts folder, we define the Solidity version and import the IERC20 library from OpenZeppelin. Remember, we must have previously installed OpenZeppelin contracts. The IERC20 library will allow us to access standard ERC20 contract functions like balance of and transfer. We define our contract called tokenlock and define this public variable IERC20 called token. We are going to declare a constants that we will need when withdrawing funds to calculate the interest generated on withdrawal. This constant that we will define as 5 for 5%, and the constant seconds in year that will serve us to calculate the annual interest, since we will make our time calculations in seconds. In this lock info structure, that will contain 3 integers, one for the amount of tokens to lock, another for the unlock time, and in the last one is to store the moment in which the funds were locked. Structures in Solidity are used to create composite data types. Now, by declaring this public mapping, lock info map, we can store in the contract account addresses with their locked amounts, unlock time, and deposit time. By relating the given addresses with an array of lock info, an array is used so that each address can have multiple locks with their respective lock and unlock times. We declare a constructor that will receive the token address for which our token lock contract will function, and within the constructor, the token variable is created, which will be an instance of the ERC20 contract, whose address we send when deploying token lock in order to interact with the tokens functions. Now we'll create the lock function, which will receive the amount to lock and the time from which funds can be withdrawn. In this function, we take the token balance of the account interacting with the contract to then verify through a require if the account contains sufficient funds for this lock, with the condition amount to be locked is less than or equal to this balance, otherwise the error insufficient balance is triggered. If the condition is met, the function continues, this time placing a new entry in the lock info mapping with the address that sends the transaction as index and the amount to lock, the unlock time, and the current time of the blockchain as the deposit time. Next, we transfer the amount of funds to be locked from the account, sending the transaction to the token lock contract. Remember that this transaction is signed with the private key of the sender, granting permission for the contract to effectively transfer their funds. We now need to create the public withdraw function, with which we can unlock the funds after the unlock time has elapsed. We create a user lock info variable that will store all the entries that are stored in memory in the lock info mapping with the address that interacts with the contract. Let's note a couple of details. First is that the user lock info variable is an array of lock info structures. That is, it can contain more than one lock made by the same account. Second, we see how the storage keyword is used. We use this to create a reference to the information stored within the contract. In this case, the lock info mapping that contains all the account information, amounts, withdrawal times, and deposit times that are stored in the contract. And by declaring it as storage, we ensure that changes we make to the variable information will be saved in the contract. With the lock deposit information of the account that called the contract, we will create a for loop which will go through all the deposits that the sender address interacting with the contract may have, and for each one perform the following operations. First, it creates a reference variable of lock info structure of the information for that specific lock. And if the network time is greater than the unlock time of that deposit, that is, if the withdrawal deadline has already expired, then withdrawal proceeds. We will implement a small interest payment system as follows. First, let's determine the number of seconds the funds remained locked, subtracting the chain time minus the time the lock was made. Now we will calculate the interest that has been generated. To do this, we calculate the interest generated per second, which will be the locked amount by the interest percentage divided by 100. That is 0.05, all divided by the number of seconds in a year. Remember, in Solidity, there are no floating point numbers, so we need to express divisions that amount to integers representing Ys. Now we can calculate the interest generated by multiplying the seconds the funds were locked by the interest generated per second. After this, we can make the transfer. By calling the transfer function available for the token contract instance we call token, with the address interacting with the contract as the destination of the funds and the withdrawal amount, which will be the locked amount plus interest. At the end, we set the locked amount to 0, marking the lock as withdrawn. Our little DeFi contract is ready. Let's compile it using Nodejs Hardhat compile, and we have this result if everything goes well. And now we will create our script to deploy this contract. In the scripts folder, we create a file called deploylock.js. We import the ethers object from the Hardhat library. We create our main function. We get the information to deploy our contract with the getContractFactory function and the name of the compiled contract. We save this information in the token lock constant. Let's define the address of our token. If you followed our tutorial on creating an ERC20 contract on the Binance Smart Chain, you will already have the address of your own token available and you can place it here. If not, kindly follow this previous tutorial link in the description so that you have your own token created, ensuring your account is the owner of that token address. We call the deploy function on our token lock constant. Remember that the constructor of our contract receives the token address, and so we will send it as a parameter. We will say the result in the token lock deployed constant. And with this line of code, we make sure to wait for the transaction to complete. And then we can display the address of our already deployed contract on screen. Of course, we call the main function with error handling. And we run npx hardhat run scripts /deploylock.js. After the process is complete, we have the address of the deployed contract. Let's copy this address and have it on hand. Now we're going to create the scripts to test our contract. First, we're going to fund our lock contract with tokens to pay for the interest. In the scripts folder, we create the fund lock contract.js. In it, we import the ethers object from the Hardhat library. We declared the addresses of both the token and lock contracts. We create the main function. We get the main account derived from our seed phrase. Remember that this account is defined in the Hardhat config file in the accounts variable, referring to a seed phrase that we get from the env environment. We are going to declare the amount we want to deposit into the contract. For now, it will be 1,000 tokens. To make the deposit, we must create an instance of the contract as we have been doing. This time, we can do it with the getContractAdd function, sending it the ERC20 parameter in quotes and the token address. This way, we can easily access the standard functionalities of any ERC20 contract. Now we can make the transfer. with funds from our wallet to the lock contract address. We connect our wallet to the token contract with the connect function, and then we call the transfer function with the lock contract address as the destination of the funds and the amount we have defined. We wait for the transaction to complete. Now let's print on screen the token balance of our lock contract using the balance of function for our token instance and the lock contract address. We show the balance on screen parsing it using the format either function. We call the main function with its respective error handling. Let's run our script with npx hardhat run script /fund lock contract.js, and we see the balance for our contract on screen. Remember that the signing account must have a token balance greater than what is trying to transfer. An alternative that we want to show to fund our lock contract would be to directly use the mint function that we defined in the myToken token contract created in the aforementioned tutorial. Remember that this mint function receives the address where the minted funds will be deposited. So if we're assigning the transaction with the account that owns the contract, that is the account that originally deployed the contract, we can use the mint function to fund any account by minting new tokens. You should keep in mind that this adds inflation to your token. Let's create a new file called minttoken.js. So first we make the corresponding hardhat requirement, and let's declare the addresses of the token contract and the lock contract that we have deployed. In the main function, we define the amount we will mint, and we will create an instance of the token contract. On this occasion, in order to be able to access the mint function, we will create this instance through the getContractFactory function, sending the name of the deployed token contract, which should be present in the artifacts/contracts folder. And then in this variable, we include the token address through the attach function in order to have our instance of the contract. Remember that getContractFactory requires the contract API. That is the binary interface that contains all the information on how to interact with the contract. And this is available in our environment since we have deployed the contract right here previously. Now we simply call the mint function by placing the lock contract address as the destination for the minted tokens. Again, remember that this will work if in hardhat configuration, the signing account is the same one that originally deployed the token contract and is the only one able to mint new tokens. We wait for the transaction to complete and print the lock contract balance, as we did in the previous script. Call to the main function with error handling. But let's test our script by running npx hardhat run scripts /minttoken.js. And we see the new token balance in the lock contract. Now, let's create our scripts to lock and unlock tokens using our lock contract. In the scripts folder, we will create a file called locktoken.js. We make the corresponding hardhat requirement. Let's put the addresses of the token and lock contracts. We create the main function. This current timestamp in seconds variable will have the current time in seconds. And for our test, we will define the unlock time as 60 seconds in the future by adding 60 seconds to the timestamp in seconds variable. We are going to create an instance of our token lock contract using the getContract function with the name of our contract as it appears in the artifacts/contracts folder and the contract address. We will create an instance of our token contract, again with the getContract function, sending the ERC to any parameter and the token address. We get our main account with the getSigners function. And we are going to print on screen the balance of our account. Let's define the amount we will lock. And we create the transaction to approve the contract to send this amount to the contract's own address, using the approve function previously connecting our signer account to the contract instance. We wait for that transaction to complete. Now to lock the funds, we access the lock function of the lock contract instance with the amount to lock and the unlock time. Previous connection of our signer account to the contract instance. We wait for the transaction to complete and we log the message that the tokens have been locked. Finally, we show the token balance of our account. After locking, we call to main function with error handling. Let's run our script with npx hardhat run scripts /locktoken.js. And we see the balances before and after locking. Now we will create our script to withdraw the funds. Let's create a new file called withdrawtoken.js. We copy the hardhat require and the token and lock contract addresses from the lock file. We create the main function and again create contract instances as we did in the previous script. we get our main account with the getSigners function. And we are going to print on screen the balance of our account before withdrawal. We announce the withdrawal of funds, and we create the transaction that accesses the withdraw function we created in our lock contract using the lock contract instance we created after connecting it to our Signa account. We wait for the transaction to finish. We show a success message and then show the new balance to confirm the process was completed satisfactorily. We call the main function with its respective error handling. Let's run our script with npx hardhat run scripts /withdraw token.js. We can see that the funds have been withdrawn successfully with the corresponding added interest. If you got here, then you know how to create a token in the Binance Smart Chain. You also know how to create a smart contract for DeFi. If you have any questions, let me know in the comments. Hit like, subscribe if you want to know more on Web3. Until next time,